last time we had a quick look at threads, how we can use them, and how we can use a log to organize which thread does which work and arrange them next to each other. We also had a look at garbage collection, which will be important today, because there will be a couple of types that absolutely require to be disposed. So this is the first time we actually have to use dispose in a real-life setting, so to speak. To get into the groove, let's start with a simple program. I'm gonna make a static method. Static void, let's just call it output. And it's just gonna do simple output from thread something. Let's skip this for now. Let's go back up here. We're gonna create some threads. Gonna just make an array. Almost, except we're just gonna forcefully put it to 3 for now. No, let's go crazy. Let's do 5. And then length less than wrong way around. I mean, that's also one way to do it, right? Count down instead of up. But for each I, that's I equals new thread. But we pass on basically a function pointer. Remember, delegates, important topic. We pass on a method as a value to this constructor, which will store that internally in a variable, in a field. It's not storing data, it's storing the information, the address where to find this method. And it's stored in such a way so that the computer knows this is not data to be used, but a method to be executed, code to be run. So we create a couple of threads, and for each thread, we're gonna just copy this over. I'm gonna call threads I.start to start all the threads. And I want to see each thread working on its own. So to distinguish these threads, you're gonna give them a name, which I'm gonna use the object initializer for. We haven't seen that in a while. And I'm just gonna give each thread a string as a name, and this name is associated with this specific thread in C#. It's stored permanently in there, and whenever I have a thread running, I can check its name, and that might help me identify it. And this is mostly for debugging, to make that easier. And you should be able to see that in a moment a bit better. But it could, in theory, also be used to identify a specific thread programmatically, because you want to associate it with something specifically. But there are other ways to do that, and this might not be the best way to use name then. And for us, it's just thread number I. It's just string interpolation. Let's add the $sign like that. So each thread in this array will get a name, with I being the number. So we start at thread 0 and go up to thread 5 for now. And output is gonna be run in each of these threads. And now we can use thread.currentThread, which is a property, a static property of the class thread, to get an instance of the currently running thread, the thread that's executing the code. If I store this, this is basically the very specific instance we have stored in this array. It points to the same thread. So for each of these 5 threads we store in this array, we're gonna run this code, and each of these threads will then get a reference to itself using thread.currentThread. Does that make sense? So this will be one of the 5 threads in this array. And that's why I can do this to get the name of our current thread and output that. Now, when I start this code, you will see that there isn't much to see. Right, actually that worked better than expected. Okay, maybe I should make that a bit clearer the next time. Let's provoke it a bit. Kinda takes away from the effect, but whatever. We're gonna pretend our output did a bit more work. It's a bit heavier load it has to take care of. Although 10 milliseconds, I mean in computer time that is a lot. We mentioned that earlier. Wait, not earlier, a week ago. A bit over a week ago already. So let's try running this code again, and maybe this time you can see it. Okay, this time it actually displayed. We ran this code, we got hello from thread number 01324. You can see immediately the same thing we discussed last time. Threads do not run in order. They just get called by the computer when it deems them worthy of being executed. It's a bit of arcane knowledge, the whole internal scheduling of computer, but it's more or less random. At least for our purposes, we can consider it random. So when I call this again, we will get a different order. Like that. And let's extend the deadline a bit more extreme. A second. There we go. Let's now set a breakpoint in here. Right after it started. Actually, no, let's not put it in there. Let's put it in here, in output. Which makes a big difference. Let's put one up here as well. Well, when you're in the debugger mode, at least in Visual Studio, you have some different views probably. So the entire debugger view looks different from the normal coding view, the way everything is arranged. You can of course change everything to how much you like it, but on the top you can see a couple of extra outputs here. One is our current process, and well, there's only one process, so that's obvious. The frame, I mean, you already know the core stack, just the stack, but this one is the interesting one, thread, because now you can see all kinds of different threads that are currently loaded in our process. And you might not recognize them, you might not understand what they are, and you don't need to. There are always a couple of threads in the background that are used by the runtime itself and by certain .NET functions without you being aware of them running. So there will always be some that you might not recognize the name of. You can also see the name is not unique, and some may not have a name at all, but you recognize the one on top here, which is highlighted with this greater than, which is the main thread, which is our introductory thread which runs the main method. Now let's go forward. The next breakpoint hit, this time inside output. And now you can see we are in thread 0. And also see we already have thread 1 and 2. They're already established as running threads, or at least as threads that are still running. Let's move forward. I just hit F5, just continue by one. We are in thread 1 now. Move forward by one more, and no output. Weird things happen. Let's break away here. Let's maybe remove the delay and put the breakpoint below. Does that change anything? 5, 5, 5, F5, and F5. This time I had to hit the breakpoint 5 times. So let's try that again on top here. 5, F5, 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 5, 5 times. That worked. Let's try to set the breakpoint here again and here. So that ran through. And let's introduce the thread.sleep again. I think we had it at 1000, right? So we're in the main thread. Now we're in thread 1. And only thread 0 exists. Once, twice, thrice, 4, 5. And weird behavior is gone. Well, that's your lesson in threading can do weird things, and the debugger can do weird things. And if you combine them, they just multiply. To be honest, I have no idea what happened there specifically. Just no weird interaction between the debugger and threads. Don't think too much about it. So, debugging, it will break in the first thread that hits the breakpoint. It will halt the entire process. So all threads are paused. And we are currently in thread 2. We can also click on thread 1 and see where it is currently set. It's also waiting in this line. Thread 0, also waiting in that line. Main thread is up here, executing this run right now, on I equals 3, which is why we only have thread 0 to 2. Thread 3 wasn't started yet. I'm not going to look at the others because we don't care about that code. Let's go back down here, continue with our code. Thread 4 is ready already. Let's go back to start. It's 5, that's fine. Let's just finish our thing. Let's do something more extreme. Thread.sleep. This time let's wait for 5 seconds. Actually, let's wait for 10. Oh, right, I never mentioned that. There are things you can make easier by introducing special characters. In case of decimal numbers, you can use underscore as a sort of decimal. Not decimal, what do you call them? Like instead of putting down a comma to indicate 1000 steps, so every 3 digits in the code, you can use an underscore as a symbol that's visible to you but completely ignored by the compiler. So to the compiler, this doesn't exist. This is just 10,000. But to us, it's 10, 3 zeros. It's a bit easier to read this way. So let's run our code again. 5, 6. So we didn't stop until all the threads stopped running. Interesting. Thing is, that's not necessarily true in every situation. So, which might make this a bad example, but this is what I should have added to make that same behavior. This will force that behavior. You might run a situation where you start 5 threads and before they even execute, your program exits. Because once we hit start on all 5 threads, this main method is done. There's nothing more to execute. So the main thread, the main method, and so the main thread is finished. The one that spawned the entire process. And usually that would mean that the entire process then begins shutting down. Because the main process is done. These threads I created, those are background threads. Just like the other threads you saw in the list that you didn't know about. And background threads are just running in the background, but just stop running once the main thread exits. That's how usually things are done. And That's what we also have this property for in a thread, the isBackground property, which by default is true. But you can also set it to false to specifically create a foreground thread. A foreground thread does not depend on a main thread running. It's basically the way it works is the main thread, the one that starts everything, is automatically a foreground thread. And everything else is by default a background thread. If I manually create a new foreground thread, we now have two major threads. The main method, the initial one, and the one we created. And the process, the Windows process, will only stop once all the foreground threads are stopped. Essentially, you determine whether or not your thread is important to the entire Windows process. We don't really need to talk about that now. It's rare that it's important, but there are some cases. For example, I use it for logging. If you want to ensure that your logs are always written, which is important, especially during times when your program unexpectedly stops, you probably use a foreground thread to handle writing those logs or storing them away somewhere safely. Not necessarily writing them, but just making sure that the data is put somewhere so it can be recovered. And at least I know for work we use foreground threads for the logging, at least for the core logging libraries, that make sure that all the logs are safely tucked away before they allow the process to shut down. Otherwise, as soon as the main method would end here, all logging would stop, and even if you're mid-writing, it would just end. And that's not a good way to handle things. But usually a background thread is fine because you're only doing some extra work that's meaningless without the main thread doing something else with it. Thread join is... Well, I'm not going to say it's the opposite of start because that would be more a killing the process, which is bad. You should never do that. I mean, killing the process in Windows, that's one thing, but killing a thread is a bad idea. We're gonna go into why later. But start would just mean, please, computer, start executing whatever I put into this thread on an actual thread now. Join would mean, please, computer, hold my current thread and wait for this other thread to finish executing, and only then continue with your stuff. So join is waiting for another process, for another thread in my process to exit. It's like, look at the simple diagram. We have our starting point. This is where we go into the program, our main method, and that does some things. And then maybe it spawns off parallel thread that runs on the side, or maybe another thread. And they all run until our main thread exits, at which they also just poof, stop. They just stop existing. Unless they are foreground thread, in which case they can continue running. But if we want those to safely exit, even though they are background threads, we can just say, hey, this one, wait until those are done. So once this exits, only then will you continue. And then maybe once this exits, continue. So in the diagram would be more like closing this up, go down. We branch off in two different flows when we create a new thread. And back down here, we join them again into one single flow. So we branch off with a thread.start. And we merge back up with join. It's pretty simple logic. You just need to understand the concept. This runs a parallel workflow, and this means wait for this other workflow to finish and do nothing until then. Just halt all processing in this current thread. So you split off into two parallel work processes and you merge two processes back together. And also important, right here, we only merge two threads. Kind of merging. We're waiting for thread, 0 for example, at first. And once that is joined, only then do we continue our loop to I equals 1, and then we make a join on thread number 1. And wait for that to finish. And only then do we continue a loop and check thread 2, and 3, and 4. So join does not mean we merge all the threads in this array. We only merge our current main thread and one of the threads in the array. But that's fine, because once the first one is finished, we just wait for the second one. And if that second one has already finished by the time the first one is done, then okay, we can immediately merge and we're done. We don't even have to wait. Because if the thread exits while we wait for another one, the instance of the thread is still valid. It's not doing anything more anymore, but we can still use that variable. We can still access its data. We can still do stuff here like getting the name. You can also check is alive to see if it's still running, or thread state if you want to be a bit more specific. But yeah, even if the thread is done, the object itself is still valid, the instance, and you can still request data from it. So if the thread is done and you call .join, it will just immediately return and you don't have to wait. So that's completely safe code here, perfectly fine. Now let's go back to log, just a quick recap. Private static, let's make it simple. Object log, and let's use initializer in here. I don't like them, but it's okay in this case. Let's want to make sure that this output does not happen in parallel. We can use the log statement, which uses our log object, the reference to our log object as a key, so that all threads can communicate about the same log. And so only one of the 5 threads, even if they all start at the same time, will be able to execute the code in this code block. Which also means we can do something like this. Console.readKey. Let's say intercept. No, let's not intercept. Let's do keychar. And we output the keychar. Okay. Now these two lines are both inside the log statement, and so only one thread can execute a console.readKey followed by console.writeLine. Let's just try that out quickly. I'm typing in an A, typing in a B, C, D, E, like that. And it actually is neatly arranged this time. What happens if I don't put that in a log? Let's try to put that outside. Pressing an A, B, C, D, E. Seems to work just fine, right? So what's the big deal? Well, the order is a bit different. Let's try to move this out of the block as well. Not have a lock at all. A, B, C, D, E. Still everything is fine. So we don't need the log, right? Let's pretend this code had a bit more work to do. Yep, that was too fast, sorry. I'm an idiot. I'm an idiot. I planned out this nice code to demonstrate something and I made a rookie mistake. I made a really bad rookie mistake. This was the code that I was supposed to write. Private static input character. Let's do it like that. So first of all, character itself is thread safe, and so far that we can read and write this atomically, so there's no conflict with that. So in that sense, this is safe code. Let's try that again. Should work reasonably well, and it does. Let's add some delay again. Let's make it a bit bigger this time. Now it's obvious what happens. I read the input, and then I wait in one thread. But then the next thread can immediately read again and overwrite the input character with whatever they saw. And then the next one can come up and overwrite the character again. Because while the other threads are waiting to use that input character, the active threads can overwrite it with new ones. And if we put this out into the log statement, only one code at a time can execute this code, and it must complete it fully before another can start. So for that scenario, okay, let's try BC. It doesn't accept the C until after it's finished. So if I press two keys and I'm only reading once, it will buffer that one key. EF, it buffered the F, so you can see it again. That's background logic from the console. But it did follow up everything in order. It did not overwrite anything in between. No issues with that. This would be one example where you want to make sure you have a log. These operations need to happen in order in one single thread. Like they all belong together. You cannot separate them and let another thread take over in between. That's problematic. That's why you put them in one log statement to make sure these are always executed together by one single thread. No thread can interfere while these are not completed, at least if you program it right. If I make another method that does exactly the same thing but without a log statement, then thread safety is gone. It's important that you as a programmer make sure that all the parts that interact with a sensitive system do have a log where needed. So if I have several methods that do this, but another method, output 2, and I had the same code, almost the same code, I would need to make sure that it also has a log statement that shares the same reference for logging. So both organize access to this particular code or this particular code using this reference, and so only one thread at a time can execute this code or this code. Either thread executes this one up here, or thread might execute this one, but the point is these 3 lines of code can never interfere with itself or with this block of code. So that's locking. And this is one thing you usually do with that. That's the most fundamental reason you have a lock statement. You need to make sure that a single thread executes several different instructions in one go without interruptions. Having a lock statement, however, is not always possible. Right now, I have these 3 lines of code that can execute right one after another. No problem. What, however, if this line of code is in one method and this line of code in another method, and those 2 methods are inside a class somewhere? And you have a larger, long-running operation that at some point needs to call this, then do some complicated stuff in the background, maybe wait for input from the outside and do some calculations, write something to the database somewhere, and then some point in the future it has to run this code. You cannot put them into one single lock statement. Maybe. I mean, I'm sure you can refactor somehow, but oftentimes you will not be able to put everything into one consistent block of code. How would you be able to recreate the same effect of ensuring that this code and this code cannot be interrupted by someone else calling this code a second time without putting it in one block? That's what we have a special type for. Let's remove the lock for now. And it has a very general name because the concept is pretty important for computer science in general. And the special object is called Mutex. I'm gonna store that in a static variable right now, so everyone can share this one mutex that I've created. And a mutex is... how do I put this? Imagine it like a token. I have several threads. Let's put it this way. Oop. You can see it. Where is it not? There we go. So let's say we have thread 1, thread 2, thread 3. And they all want to access a certain resource. But this resource can only be used by one thread at a time. And this resource might instead be a certain code, well, not a certain sequence of instructions, let's put it that way, that have to be executed in one order and not be interrupted. What they can do is they use a mutex that they all can see, and they just request a token from this mutex. They all make a request to the token, to the mutex for a token, and then one of these threads, and only one, will receive a token. And only this thread then can execute and actually get access to that resource. And once they're finished, it will then return this token to the mutex. It will have to explicitly return this. This is important. It's not automatically happening. You have to give your token back to the mutex, so then the mutex can pass on the token to someone else that then has access, that then itself has to return the token. Until the last one has the token, is finished, returns it, and now the mutex just has a token lying and is waiting for someone else to request it. And the important part is that there's only one single token available and only one thread can receive that. And that's how we can ensure that only one thread accesses the resource at a time, because it's only possible for one token to exist, at least in one mutex, So only one thread can possibly have a token at any given time. And that's what we get with the Mutex. The Mutex can then make a yeah, let's do wait one. Simple wait one. So with that, we tell the system, I want a token. This is your request to the Mutex. I request a token. And it's not a request and instead of wait one, because we wait for this token to arrive. If the Mutex currently doesn't have a token available because it already gave the token away to some other thread, we will just be put on hold in here. And this instruction will halt at this point and wait for the Mutex to free or wait for the other thread to free the token, give it back to the Mutex, so the Mutex might pass it on to us. Or another thread that's also waiting, because just as we are waiting right now, another system, another thread might also be waiting on this Mutex, waiting for their chance. At some point, usually it happens in a queue, at some point we will get the token, and then this method will exit and our code continues. And I shouldn't have removed the input character. Private static. Yeah, so that code works. And once our code is done, you can just go mutex.release mutex. And with that, we release our token. Again, it's not a literal token, but it's the best way to explain it. Just imagine someone passing a ball around and only the person with the ball is allowed to do something. Or maybe only one person gets the key to the copier room and is allowed to make any copies. Or print something. I think that's more applicable maybe. Only one person gets the key and everyone else has to wait for that person to return with that key to pass on to someone else. And because there's only one token available, it is extremely important that this code gets executed, no matter what. If we receive the token up here, we have to release this. Under no circumstances can we just leave the Mutex open like that. I mean, it's absolutely doable, like it's easy, just don't call this code, but then everyone else will get stuck on this line. And they will never continue. That brings everything to a complete halt. Bad. Very bad. That's why we have usually a try finally, which surrounds our code, and then in the finally releases our Mutex. So no matter what happens in here, we know this code will be called. Either this just finishes, then it will be called, or this will have an exception in some form, something will break, and we just release. We might still throw the exception further up, sure, but we'll release the Mutex so other threads do not break just because we broke. That's important. And this is a pretty common pattern. You make a request in one of these, what's called synchronization tools, instances. You request something, you request a resource, and then you have a finally block that ensures you release that resource again. And this is, of course, only in a single code. Gets a bit more important if you have class example. Let's say this stuff here is actually inside our class private read-only mutex. Let's do public example. mutex, just like that. And yeah, let's call it run, whatever. Text dot wait one. Try finally. Text dot release mutex. Save call. And then we make a new example. Pull.run. So we can do it like this as well. Actually, let's just copy the code from... No, let's not copy that code. Let's just use it as is. Skip the output. That should work as well. Everything works here, right. So I can run this, get 5 save calls, and all of them are securely stuck inside a mutex. So only one output can happen at a time, which, I mean, of course, in of itself not necessary, we already know that, but this is how we would use a mutex. Mutex, however, can be disposed. It's one of those types that you will use that itself are disposable, which means our class that stores a mutex must be disposable as well. I mean, it doesn't really have to be sure. In theory, we don't have to do that, but it is the right thing to do. Like, it'd be really weird if you store an disposable yourself in your class, but do not have a way for someone to dispose that by disposing you. So this is one of the cases where you are disposable yourself and you implement a dispose method that at the very least calls the dispose method of whatever you're storing. So this makes a save call. Actually, we can do thread.sleep. Let's do 100. This should also demonstrate just the whole, make sure they both happen at the same time. You can always see a call and an end. If I were to put this outside of the mutex, we can see all the calls happening first and then all the ends. So this is another case of make sure these 3 lines are executed in one go without interruptions. Exclusive access to the console. So yeah, mutex. For now, this is essentially the same functionality as our log. No big deal. But mutex can do some interesting things that you cannot do with a simple log. First of all, we can split this into 2 methods. You could have one method that makes public void. And for example, we could have another method that makes the mutex.release mutex. And the run method makes the wait one. So in theory, construct like this, well, not this one exactly, but similarly might exist, where one method requests the token and a different method has to return the token. Couldn't do that with a log. But there's another cool thing that mutex can do, which we have to set up in the constructor. We have a couple of parameters, which I know you cannot see. So for some reason the IntelliSense is not picked up by OBS. Not sure why. Probably because it's... that must mean it's rendered in a different... Interesting. Okay. Anyway. It has a couple of optional parameters. And the first one would be just a boolean that I can set as true or false, initially owned. which just means if this mutex is created, do we assume the token is available or not? And you would usually start with false. There would be very specific circumstances where you start with initially owned set to true. We'll just assume you set it to false. The second parameter is more interesting. It's name. Similar to threads, we can give a name to a mutex, which can help us debugging. Like we can look at a mutex, check its name, and then know, oh, that's that specific purpose, which is convenient and all. But it also lets us access a mutex without having direct access to it. Let me demonstrate. No, I can't demonstrate easily. Okay, what I mean by that is, right now, I'm storing mutex as an instance of mutex, and my code just uses that very specific field. They all use the exact same instance of mutex. But in theory, we could have different instances of mutex that all use the underlying system resources to evaluate that one token. So even though you have a different instance, they all share the same resource internally, where you as a programmer don't see it. You just know internally they all communicate with one another and they sort out the token. I can create another mutex. Mutex2, that. And mutex, just give it some string here. Mutex. And now I'm using the same name for both of them. And the system would now use the same token that is shared between the two. Inside your C# program, that's not really relevant, but the cool thing is, this is not necessarily intended for your own program. This is intended for sharing a token between two different programs. If you give a token, if you give a mutex a name, it is now available as a resource in your Windows system. Honestly, I'm not too sure how it is handled on different operating systems. I assume the same fundamental idea is handled just in a different way by the runtimes. But essentially, you register this name inside your operating system as, this is now a mutex, please take care of that. Make sure that all processes that use this mutex with this name have only one token between them to share. So if one thread in my program waits 1 and receives the token and executes, then all other Windows programs that use the same mutex do not have access. It is as if all of us running in the same program and the same process using the same instance, as if we're all sharing the same log statement, so to speak. But we can do that across processes between different programs. You might not come across that situation often, but it is incredibly useful if you know it exists for some very easy synchronization between entirely different processes. I definitely have to use it myself a couple of times. Also, for work, there were a few things where, no, there still are things where the mutex is super useful for shared resources between processes. And for that reason, there's also a last parameter, Boolean, an optional one that you can add, which gives you some information. Namely, am I the first person to register this name? If so, then this Boolean would be true. But if someone else already registered this mutex with the operating system and is actively using it, then this will be false. And that way I can tell whether or not am I the first one to use that, or do I have to share a resource with at least one other program. So, mutex, we can split the request and the release into different parts of the code instead of having everything forced into one consecutive code block. And it allows us to share a lock, so to speak, with other processes. If we need to. I mean, if I leave this out, it's gonna be an anonymous mutex. It's just gonna be purely internally in my process only, and that's fine too. Just pretty simple thing if you don't name it, but might have its usages. Depends on what you need to do. Now let's go a step further. What if this mutex didn't have just one token? What if it had two? What would that mean? If it had two tokens and one thread requests a token, it would still have another token left for a second thread to request. Not all three threads would be able to get a token, because there are only two in total, but there would still be the option for two threads to run in parallel for the same resource. And you might think, what's the point of that? I mean, then I still have two threads running in parallel, and that's the whole reason we want to have this mutex in the first place, right? Why do we allow suddenly two processes or two threads to run in parallel? Well, maybe the point isn't to protect a certain part of the code from being executed in parallel. Maybe it's just to organize a limited resource which can be used thread safe. Limited but thread safe resource, let's put it that way. Something that you can absolutely execute from various threads at the same time without any conflicts, but maybe it just takes a lot of resources. And you want to put an artificial bottleneck in your system, so you reduce the amount of resources you use as a process as a whole. You want to throttle a bit. Just as an example. To allow that to happen, there's a different data structure, which we can use almost the same as a mutex. And it's the Semaphore. Let's rename this Semaphore. And we'll take care of that in a moment. A semaphore requires at least two arguments from us. The first one is an initial count, and it's similar to the Boolean we had earlier with the mutex that tells us if it is owned or not. We're just going to set it to 0 for now. And the second argument we have is the amount of tokens it has, which we can set to just 1 for now. Maximum count is 1, initial count is 0. That means we have at most one token to give out, and right now no one owns any tokens. You can still use wait1 to wait for a token to be free, to request access. Only instead of release mutex, because we're not mutex, we just have release. And this code can already run, so we can have the starting. And why is it not? Oh, right, sorry, my bad. Initial count should be 1. Wrong way around. I did the wrong way around, sorry. So yeah. Initial count is, if this was 0, that meant someone already took the token. Initial count is how many tokens are currently available, how many are available at most. That's how it is. My bad. Today is not... Okay, it never is my day. Should probably not stop saying that every single time. So right now, this behaves exactly like a mutex. There's one token available, we request that, and everyone else has to wait until we release again. But I can also increase this to maybe 2, 2. Now I have 2 tokens that I can hold in this semaphore, and 2 of them are free right now. So I just run this code and 2 calls happen at once because 2 threads can run in parallel. There again, 2 calls at once. Let's increase it a bit. Let's go to 4. 4. We can call 4 times immediately, but the 5th one has to wait for at least one of those to exit first. We can also increase the maximum count, of course, to 5 directly, but because only 4 are available in the beginning, it's not really changing all that much. By the way, if I start with a higher count than maximum, we get an exception, because that's not allowed. You can only hold as many tokens right now as you are available to hold. So if I put this to 5.5, we have basically complete parallel processing because every single one of our 5 threads gets a token. And just like Mutex, Semaphore has some additional arguments, the first one being, again, a name. And the same system as with the Mutex, this allows us to share the Semaphore, the available tokens, with other processes. Exactly like Mutex. So if you just imagine the logic of a Mutex being the same as the Semaphore with 1-1, that might be easier. Just remember how semaphores work and just imagine a Mutex is one that's limited to 1 token only. It's more a special case of a semaphore then. Though initially the implementation works a bit differently. They are not the same, but they're also kind of the same. I mean, functionally it is the same. And just like the Mutex, it also has the out variable created new, which lets you know if another system already registered the semaphore as a resource in the operating system. So that's useful. And by the way, if you know that you don't need to share the semaphore with other processes, which you probably don't need to do in most cases, you can use a different class instead and use Semaphore Slim, which is a bit more lightweight. You can share it with other processes and it's intended for a quick, it's only my process, just quickly manage these few calls and be done with it. So personally, I almost always use Semaphore Slim. The Mutex I actually used for operating system level organization between different processes. I never had to use a semaphore really for sharing between different resources, sharing resources between different processes. So maybe consider using Semaphore Slim, which should be a bit more performant in theory, but there's no harm in using Semaphore directly. Just remember, all of them need to be disposed. And all of them have to make sure that at some point we release. In my case, that's pretty easy because I do run the code in one go, so I can just put try finally down. If your code separates a bit, well then maybe include a boolean. Nope, that's not what I want to reach. Private bool. Spoken, let's put it down here as spoken false. Or wait. Token equals true. Can do something like this and then if has token. Yeah. You could do something like that to make sure that when you dispose, you release the semaphore you might be holding if you don't do this immediately after that. Just something to be aware of, something that's important to keep in mind. Alright, so that's those statements. There's one last structure I want to look at. And it has to do with something we tried last time. Imagine a situation where different threads have to wait for some other thread to be done. Remember, we used a couple of logs to make sure that only one thread can execute a certain amount of part of the code. And in that code, we checked if a certain counter was at a specific value. And only if it was, did we execute some code. And if it wasn't, we just continued, started back in the loop, queuing back up for a log statement to get access again. It was just very simple, inefficient but effective method of making sure that threads execute certain code in order. And the annoying part about that was performance, because in the beginning we just had an endless loop that was constantly queuing up in the log with a normal log statement, trying to get access to the code, then checking if a variable, or a field specifically in that case, had a specific value it was looking for, and if not, it would just jump back to the start using the loop, log back up, check the value, go back up, get into the log, check the value, all the time. And that wastes a lot of resources, especially time, because every time you log to check the value, all the other threads have to wait before they can check the same value. And that makes everything just slow and take a lot of resources in general, because their CPU is just constantly spinning. Also, thread changes are... You know what, let's not get into that. But our way around that performance issue was so thread.sleep, to make sure that we don't immediately queue back up to get access to the log. So we would check if the value was the correct one. If not, we would just wait a bit and then check again. So we don't constantly check, because that was fast enough. But that means, of course, we do lower the possible reaction time. And there's a certain data structure that allows us to swap the logic around, the flow of data. Instead of just polling, that's what we would call that, instead of just checking if a value has reached a certain target, and then checking again, and checking again, and checking again, we can just put our thread on hold and tell the system to just give us a call when something new happened. Instead of constantly checking if something happened and if that something is the correct thing we're waiting for, we just wait and let ourselves get contacted by the system when something specific happened. We're waiting for a certain event to happen. And until that event happens, we just wait. That means if nothing happened, we don't have to check anything and we are not wasting any resources, because we don't do anything. And on the other hand, as soon as that event happens, we are getting contacted and there's no chance of just wasting milliseconds in a thread.sleep because we wanted to be more efficient. Like, we don't lose any reaction time and we don't lose any resources. And for that, we're introducing something else here, and that is the EventWaitHandle. Like that. What is going on? Why can't I? Ah, switch keyboard layout. Okay. I forgot the underscore in the beginning. EventWaitHandle. It's new EventWaitHandle. Let's ignore that for now. Let's change this code a bit. And introduce... Now let's just do it like that. Instead of, so for wait, we're gonna do EventWaitHandle dot wait1, like before. And then we do our code. Also, let's do this one public, because we'll do something with it. So, EventWaitHandle, we have, just like with the Mutex, basically a Boolean that can determine if the... No, wait, it's actually not. No, that's not a good comparison with the mutex. This has a very different meaning. But, let's go back to the drawing board. That might be the easiest. So, let's say all our threads waiting at the starting line, and they all want to execute some code. They start running, they start running, they start running, and then there's some important event here that they wait for. Something important has to happen before they can actually continue working. And the EventWaitHandle, very basic EventWaitHandle, can now set a simple true or false, simple flag, and that will wake up all the threads that are currently waiting. And they will now check, is this flag now set to true? If so, we can continue. Well, actually it's the other way around. We set this flag to true, and that will cause the threads to wake up and check again and see that it's true, and we can continue. Well, unless you include timeouts, in that case it's the event first. Well, a certain event happens and the threads check if the flag is set to true, and if so, they continue executing. And there are two ways we can do that. Either this flag just stays at true and all the threads that were waiting just continue running in parallel. Or we can set it so this flag gets set to false as soon as one of these is starting. So the others do not get to see a flag set to true and keep on waiting. Until some other point later, we set this flag back to true and trigger the event, and now these two threads can still check, is it to true? If it is, maybe this one sees it first and starts running and also sets it to false. And this one has to wait again until we set it a third time, in which case this thread backs up, sees the flag set to true and can run and reset the flag to false so no one else can do it. This first Boolean we enter here, that is the flag. Do we start with the flag set to true, or do we start with the flag set to false? Do we allow threads to run initially, or do we want them to all wait initially? We want them to wait for now. The second argument is the selection of the mode we want to use. It can be either manual reset. That means once this flag is set to true, it stays at true, and all the threads that were waiting for the event just start running. Alternatively, we can use auto reset, which means the first thread that sees it set to true will start running, and only that thread will continue running. All the other threads stay sleeping, so to speak. It's similar to the idea of the token, only it's not a token, it's just only one thread gets to see the flag set to true, and the others still see it at false. It's not that we pass out a token, it's just that only one thread gets the signal. Versus all threads get the signal. And I can just at some point determine, nope, this is enough, I set the flag back to false. And right now, when we use manual reset, once this signal comes in, this wait is over, and all our threads will execute this at the same time. Not ideal. So let's use auto reset, so that only one thread will pass this line of code. Wait one, it will wait for the event. It will wait for someone to trigger the event and it will see the flag is set to true and will start running. But this is only one thread that saw the flag set to true. We can now add in the finally here, just to make sure that something happens, EventWaitHandle.set, which is the method we use to trigger the event and set the flag to true at the same time. Calling this method will trigger all the waiting threads. Every single thread that is stuck in wait 1 will react to us setting the flag to true, and depending on our setting, either all of them or just one of them will continue running. So for us, that means the first thread that passes this wait 1 will then trigger the next one to go in. And that will then trigger the next one. And that will trigger the next one. Also, just like the others, we have to dispose the event wait handle. And that means we have to, at some point, set this ourselves to start the chain reaction. So all these threads are waiting. You can actually thread.sleep. We'll wait for a second. So the first second nothing will happen. All of them will be stuck in here, and then they will start to call that execution. So it waits for 1 second, and then all of them execute, one after another. If I don't set this, we'll just eternally get stuck here, because all the waiting threads are waiting for an event that's never arriving. And if I change this to manual, well, we get actually a couple of issues, but let's just change this code for now, and we see that all of these calls happen once, of course, because once the flag was set, it's never reset, so all waiting threads get a pass and continue running, and then all of them set our flag to true again, which is not a problem directly because it's not breaking anything, but it's kind of messing with the logic. So what's more interesting would be probably a reset, because that means once our code ran through once, no other threads that attempt to run later can do so. Will have no effect on us because we have the thread.sleep, so all our threads will run through here once, but this would be the other way around. Once you execute your code, you make a reset to make sure no one else can run. And we could put the entire thing here inside a lock statement, so only one thread at a time can wait. And that way we can mimic the behavior of the auto reset while using manual reset. So we just make sure this code is itself locked away. So the first thread that gets access to the lock is gonna keep the lock open because it's stuck inside the lock block, waiting. And only once that is finished, will it actually free the flag again, and another system can come in the lock and execute. Doesn't make too much sense, but that's one way to do it. Alternatively to passing on the parameter here, you can also call a specific subclass, manual reset event, or auto reset event, which is just the same, just limited to one of the parameter values. So let's go back to EventWaitHandle. To reset, that's it. And the same as the usual, we have a name to share it with other processes and a boolean to let us know if this was the first time we request this wait event handle. By the way, wait handle in of itself, we could make it this, is a class that is used in a couple of different ways. Wait handle is pretty important. There are many different systems that use wait handles, different types of wait handles. And the event wait handle is only one of them. Just as a heads up, if you see somewhere in the code, maybe there's a property to get access to the wait handle, there are a lot of things we can do with the wait handle. If you see the code, for example, wait1 is a method in wait handle. Reset isn't. Reset is specific to the event wait handle, but the wait handle you can wait for. Just an example. So that's event wait handle. If you want to make sure that certain amount of code waits until an event happens. Alternatively, it would be polling, where you just constantly check, do I run, do I run, do I run? Which might actually be the best solution for some niche cases, but usually, personally at least, I prefer to have that event driven. If I don't have to have the thread constantly checking something, just have it react to the event. Of course, all of that is for classic thread programming. The rules change quite a bit once we go to asynchronous programming, async await tasks, which I'm not sure we even get into because that is such a big important topic where I don't think I know enough to confidently teach you the correct way to use everything. Maybe you should make an off-topic stream at some point where I just show you generally how to use it. Best practices I picked up, but I don't think I will ever be able to teach that topic. It's just too complex. It's too easy to make mistakes, and I don't want you to make my mistakes again. Yeah, threads. I think that topic is done. Homework. Oh, here's a good one. For your homework, use a mutex as a basis, as a fundamental data structure you can use, and then create a class that mimics the behavior of a semaphore. Recreate the class Semaphore by using only a mutex. Try that. And once you're done with that, try to recreate a mutex using an event wait handle. And then use that mutex to power your semaphore. So your own mutex to create your own semaphore. And if you're not bored by that, try to recreate a system that can mimic the event wait handle just with a lock statement. Which is not going to be very efficient, because you probably only have the lock statement left for you then. But then you have the full way. Use a lock statement to mimic the behavior of an event wait handle. Very badly performance-wise, but just mimic the behavior of it. Then use that to recreate the behavior of mutex. And use that to recreate a semaphore. And you don't have to worry about multi-process sharing or something, just very basic inside your own code. That's your homework. Go from lock to event wait handle to mutex to semaphore. Good luck with that. See you next time.